Now we continue with lecture 20. In the previous lecture, we defined regular singular points and we discussed special equations, Cauchy-Euler equations, and how to find their solutions around regular singular points. And now we are going to discuss general series solutions near a regular singular point. So we have linear equation with variable coefficients. Homogeneous with regular singular point x0. Let me label this equation with star. Now we are going to consider, since x0 is a regular singular point, this means limit as x approaches x0 of x minus x0 times function q divided by function p is a real number alpha, and the limit as x approaches x0 of x minus x0 squared times rx divided by px is another real number, say beta. And using these numbers, alpha and beta, we can consider the Cauchy-Euler equation. X minus x0 squared y double prime plus alpha times x minus x0 y prime plus beta times y equal to 0. And let me label this as equation double star. So, of course, our equation star doesn't have to be a Cauchy-Euler equation. But in a way, we consider the two equations close. Okay, so we consider equations star and double star to be closed, in the sense that, in which sense they are closed? They are closed. If you consider the Taylor series, the numbers alpha and beta are the same. The limits in your equation star, alpha and beta, are the same limit as in your equation double star. So Taylor series of the solutions have the same first terms. I know this doesn't make much sense to you now, so think of this as a formal mathematical statement. This limit being alpha, it's about, so it is like, okay, the function px is like 0 at the point x0, so we have a singular point, but the 0 is of first degree. So when you multiply px with x, when you have px in the denominator, you multiply the numerator with x minus x0. So in other words, divide px by x minus x0. Then the first term, you have a non-zero first term, which is alpha. Okay, not exactly the function px, but the function qx over px. That's your coefficient function. And the same thing for the other coefficient function, rx over px. um, they have, the order of the singularity, let's say, at the point x0 is a second order, so that when you multiply with x minus x0 squared, you get a number. And y square, in this case, because that's the function itself. For q over p, that's the coefficient of y prime, so the first derivative. So if the function itself has a zero of a second order, then the derivative has a zero first order. So for q over p, you multiply with x minus x0. For r over p, you multiply with x minus x0 squared. If what I'm saying doesn't make sense to you, don't worry about it. This is some theoretical background reasoning under what we are going to do. So we will find an appropriate power series so that when we multiply the solutions of double star with this series, we get solution of star. So given this equation, we find the numbers alpha and beta. Since x0 is a regular singular point, we have the real numbers alpha, beta. Using those numbers, we construct the Cauchy-Euler equation, find the solutions of the Cauchy-Euler equation, and then find this power series so that when we multiply the solutions of the Cauchy-Euler equation with this power series, we get solution of our own equation. So let me write down those steps. Find alpha and beta, construct Cauchy-Euler equation, using this alpha and beta, as solve Cauchy-Euler equation, solve Cauchy-Euler equation to get, solve the Cauchy-Euler equation, find power series to multiply I'm having trouble with the arrows. Find power series to multiply with the solution in part 3. Finding the power series, again, this is like the previous, not the previous, the one before, the lecture about power series solutions around ordinary point. So we write the power series, and then we take the derivatives, substitute into the original equation to find the coefficients. Okay. All right, but so for step 3, we have the characteristic equation. Lambda squared plus alpha minus 1 times lambda plus beta equals 0. right? If you remember the previous lecture, how to solve Cauchy-Euler equation, we use the substitution x minus x0 equals e to the t to convert it into linear equation with constant coefficients. And for that equation, we write the characteristic equation. It happens to be this equation, lambda squared plus alpha minus 1 times lambda plus beta equals 0. This equation is called the indicial equation of the original ordinary differential equation star. Remember, our aim is to solve the ordinary differential equation star. Okay, so this is called indicial equation. Now, depending on the solutions of this indicial equation, we get different types of solutions. So, now what type of solutions? We may get two distinct real roots, we may get a repeated real root, or two complex roots. We are only going to consider the case of real roots. Complex roots can also be taken care of. You can find, if you're interested, you can find the discussion in your book. But you see, this case of having a regular singular point is complicated enough, and the solutions of the indicial equations continues to keep complicating it. So we are only going to consider the most simple case of a regular singular point, although the other cases can be treated similarly, and you can find the treatments in your book. So first, we're only going to consider the case of real roots. Say the roots are lambda 1 and lambda 2, and lambda 1 is the larger root. Of course, in case of repeated roots, they may be equal. But if distinct, we take lambda 1 to be the larger one. And we are only going to consider the case lambda 1 minus lambda 2 is not an integer. There are, as I said, there are examples in the book, there are treatments, and if you're interested, you can check the examples in the book to see what goes wrong when this difference is an integer. So when it is not an integer, in this case, what we will do, we will take y1, y2, independent solutions. No, I'm sorry. Okay, so is not an integer. This means we are in the case of two distinct real roots. So solutions of Cauchy-Euler equation I'm not distinguishing whether x is greater than x0 or less than x0. So I'm going to take absolute value of x minus x0 to the lambda 1 and x minus x0 to the power lambda 2. Okay, so these are the solutions of the Cauchy-Euler equation. So we will find solutions y1. We take the solution of the Cauchy-Euler equation and multiply it with a power series. And for the second solution, we take the second solution of the Cauchy-Euler equation and multiply it with another power series. Okay, so finding the solution means find coefficients a(n) and bn. All right. Now, the second case, when if lambda1 minus lambda2 is an integer, including the case when the difference is 0, double root, you may have a double root, then y1 can still be found, but y2 may not exist. We may need a logarithmic term for the second solution. We are not going to cover this case. Okay, so I'm just going to give you, I'm just going to consider the first case. Just as a note, in case 1, for the solutions y1 and y2, a0 and b0 will be free. So we can write the general solution as a0 times y1 plus b0 times y2. We will take a0 to be 1 to find y1, and b0 to be 1 to find y2, and write the general solution as c1 y1 plus c2 y2. You see, y1 and y2 are explicit solutions, not the general solution, but just one solution. So we are allowed to take the number a0 to be 1. It will give us a solution. And for the second one, we are going to take b0 to be 1 to find the second solution, and then write the general solution as their linear combination. Okay, let's consider our example. So this is the only example I'm going to consider. So solve the equation 2x squared y double prime plus 3x y prime plus 2x squared minus 1y equal to 0, centered at the point x0, which is 0. So we try to use this discussion to find first solutions of the Cauchy-Euler equation, and then to find solutions y1 and y2. And we are going to do this around the point 0. So first, we need to check that x0 equals 0 is a regular singular point. My coefficient px is 2x squared, qx is 3x, and rx is 2x squared minus 1. So I need to check, first of all, is it singular? Q over p, 3x over 2x squared, so 3 over 2x, not defined at 0. And r over p, 2x squared minus 1 over 2x squared, not defined at 0. So it is a singular point. Now, is it regular? So I need to check the limit x goes to 0 of x times q over p. X times q over p is 3 over 2x. X cancels out, so this gives me 3 over 2. So that's my alpha. And then I need to check the limit as x goes to 0 of x squared r over p. So x squared, 2x squared minus 1 over 2x squared. So x squared cancels out. X equals 0 gives me minus 1/2. And that's my beta. So it is a regular singular point with alpha equals 3/2 and beta equals minus 1/2. Arrows. Okay. So x0 equals 0 is a regular singular point. With alpha equals 3/2, beta equals minus 1/2. So I just write my initial equation. Lambda squared plus alpha minus 1 times lambda plus beta equals 0. So lambda squared, alpha is 3/2, minus 1 is 1/2. So 1/2 alpha minus 1/2 equal to 0. If I multiply both sides by 1, I have 2 lambda squared plus lambda minus 1 equal to 0. So lambda equals, if you use the quadratic formula, you get the solutions minus 1 and 1/2. So my first solution is 1/2. It's larger than the second solution, minus 1. Lambda 1 minus lambda 2 is 3/2, not an integer. Now, in general, we need to take the absolute value, but to make things simple, we are going to assume that x is greater than 0. X less than 0 is similar. So let's say we are looking at a solution for on the interval x greater than 0. Okay, so the first solution y1 should be x is positive. So I take x to the power lambda 1. And what is lambda 1? Is 1/2 times the power series, an x to the n, or n from 0 to infinity, an x to the n plus 1/2. So to find this power series, we take the derivatives and substitute into the original equation. When you're taking the derivatives, be careful. You see this thing here is not exactly a power series because the powers, so this goes like a0 times x to the 1/2 plus a1 times x to the 3/2 plus a2 times x to the 5/2 and so on. But when you're differentiating, again, we can differentiate term by term. So the first derivative, but when you're differentiating, the first term is not constant, so your derivative still starts from 0. So n plus 1/2 an x to the power n plus 1/2 minus 1, so n minus 1/2. And the second derivative, again, when n equals 0, the power is x to the minus 1/2. Remember, x is positive, so it is defined, x to the power minus 1/2, not constant. So the second derivative, again, starts from 0, n plus 1/2, n minus 1/2, an x to the power n minus 3/2. And now substitute into the equation. And what was the equation? Let's remember. 2x squared y double prime plus 3xy prime plus 2x squared minus 1y equal to 0. So let's substitute. So the second derivative here, we multiply with 2x squared. So n from 0 to infinity, 2 n plus 1/2, n minus 1/2, an x to the power. When I multiply with x squared, this becomes n plus 1/2. Then plus y prime, I multiply with 3x. So I multiply y prime with 3x. N from 0 to infinity, 3, n plus 1/2, an, x to the power, n plus 1/2, because I multiplied with x, so the power becomes n plus 1/2. Now, for the last term, I first multiply y with 2x squared. So what is y? N from 0 to infinity. I have a 2 here, an, x, n plus 1/2, but when I multiply with x squared, n plus 1/2 becomes n plus 5/2. And then minus y minus n from 0 to infinity, an x to the n plus 1/2. This should be equal to 0. Okay, so let's simplify. First, we look at powers of x. Powers of x is n plus 1/2 in all the series except this one. So to make it 1/2, I need to bring the power down by 2. So that means I take the index up by 2, n from 2 to infinity, 2. Then an becomes an minus 2, and n plus 5/2 becomes n plus 1/2. Okay, so all the powers now, and x to the power n plus 1/2, but this series starts from 2, so the other series starts from 0. So I need to write the terms for n equals 0 and n equals 1. So let's start with this one. For n equals 0, I get 1/2 minus 1/2, so minus 1/2, right? A0 x to the power 1/2. And then plus for n equals 1, I get 1. 1 minus 1/2 is 1/2 plus 2 is 1. 1 plus 1/2, 3/2 a1 x to the power 3/2. Plus, now the remaining terms starts from 2. I'm going to collect the, okay, let me write it down. Now, take the next one, so plus. Now take this one, the term for n equals 0. 3/2 a0 x to the 1/2. And then plus the term for n equals 1. 1 plus 1/2, 3/2, 9/2 a1 x to the power 3/2, and the rest n starts from 2. And the next one, n starts from 2 already. And the last one, I have minus sign. The term for n equals 0 is a0 x to the power 1/2 minus the term for n equals 1 is a1 x to the power 3/2, and then minus the rest, n starts from 2. And this whole thing is 0. Now, you see, if you collect the terms x to the 1/2, they add up to 0. So that's why the number a0 is going to be free. There is no condition on the number a0. Okay? For the terms x to the 3/2, I have 3/2 here plus 9/2, so 12/2, which is 6, then minus 1. I have 5a1 x to the 3/2. And in the rest, n starts from 2. So if you combine the terms, we have terms with an, 2n plus 1/2, n minus 1/2, and then plus 3n plus 1/2. The next one is not an minus 2. Let me look at the last one, minus 1, an, and then 2an minus 2. And the power is x to the power n plus 1/2. And that's equal to 0. Okay, so from the first one, we have, since this whole thing has to be equal to 0, we get a1 equal to 0. Remember, a0 is free, so we take a0 equals 1. And the rest, this coefficient has to be 0. Let me multiply this out, n squared, so 2n squared. N's cancel out, minus 1/4 times 2, minus 1/2, plus 3n plus 3/2, minus 1, an, plus 2, an minus 2, equal to 0. This is for n greater than or equal to 2. So an is equal to minus 2, an minus 2 divided by, if you simplify this, the constants cancel out, we have 2n squared plus 3n. So we just compute a few. We already take a0 to be 1, a1 is 0, so what is a2? If you take n equals 2, a2 is minus 2 a0 divided by n equals 2. So 4, 8 plus 8 plus 6, 14. So this is minus 1 over 7. Remember, A0 is 1. A3 is going to be minus 2A1 over something. But remember, A1 is 0, so A3 is 0. A4 minus 2A2 divided by, I'm taking n equals 4, so 16 times 2, 32, plus 12, 32, 44. So minus 1 over 22, A2, but A2 is minus 1 over 7. So this is 1 over 154. A5 similarly is 0. A6 minus 2A4 divided by, if you put n equals 6, let me see, what do I get? A6 something, and if you substitute A4, this comes to minus 1 over 69, 30. A7 is 0 again, and so on. So my first solution, y1, is x to the 1/2 times the series. I take x0 to be 1. A1 is 0. A2 is minus 1 over 7, x squared. A3 is 0. A4 is 1 over 154, x to the 4. A5 is 0. A6 minus 1 over 69, 30, x to the 6, and it keeps going. The first 4 terms are like this. So that's my first solution. You see, I have a power series centered at 0, but I multiply it with not a polynomial really, a power term, x to the power 1/2. And this 1/2, remember, comes from the initial equation. That's solution for the initial equation. So that's my first solution, y1. Now for y2, I use the second solution, minus 1/2. What was the second solution? 1/2 and minus 1. Yes, the second solution was minus 1. So I take y2, x to the power minus 1. Remember, x is positive, so x to the power minus 1 is defined. And the series n from 0 to infinity, bn now, bn x to the n. So n from 0 to infinity, bn x to the power n minus 1. So since the solution is an integer here, we need to be a little bit careful. For n equals 0, I have b0 x to the minus 1. But for n equals 1, I have b1 x to the 0, which is 1. So the next term is constant. b2 x, b3 x squared, and so on. So the first derivative, the first term is not constant, so the first derivative again starts from 0. N minus 1, bn, x to the power n minus 2. So this is minus b0, x to the power minus 2. Wait. For n equals 1, we don't have a term because n minus 1 is 0. You see above, the second term is b1 constant, so the derivative is going to be 0. And then next term for n equals 2, I have b2 and x to the power n minus 2 when n is equal to 2, x to the 0 is 1. So second term is again constant, but the first term is never constant. And the next term, n equals 3, 2, b3, x, and so on. Okay, so y2, second derivative, again, n starts from 0. because the first term is not constant, n minus 1, n minus 2, bn, x to the power n minus 2. So substitute into the equation. Let's remember the equation. What was the equation? 2x squared y double prime plus 3x y prime plus 2x squared minus 1y equal to 0. I'm not going to, well, okay, let me do it. All right. So the second derivative we multiply with 2x squared, and 0 to infinity, 2 n minus 1, n minus 2, bn, x to the something wrong. Yes, this should be n minus 3, right? I'm taking the derivative. So derivative of x to the n minus 2, n minus 2 come down, the power is n minus 3. So here the power is n minus 1. Plus the derivative, we multiply with 3x, and from 0 to infinity, 3 n minus 1, bn, derivative x to the n minus 1. And then the function y itself, first we multiply it with 2x squared. So n from 0 to infinity, 2 bn, x to the n plus 1. And then minus, we take the function bn, x to the n minus 1. So this should be 0. So again, only in this term, the power of x is not n minus 1. I need to bring it down by 2. So I write this as n from 2 to infinity, 2 bn minus 2, x to the n minus 1. And again, I write the terms for n equals 0 and n equals 1, and the rest n starts from 2. So let's look at the first series. For n equals 0, we have 4b0 x to the power minus 1. For n equals 1, the term is 0. So we don't have a term for n equals 1. And the rest, n starts from 2. And the second one, for n equals 0, we have minus 3 b0 x to the minus 1. For n equals 1, again, the term is 0. We don't have a term for n equals 1, and the rest, n starts from 2. And then the next one, n already starts from 2. And for the last one, if I take n equals 0, I have b0 x to the power minus 1, and the rest, n starts from 2. So again, if you look at the terms, x to the power minus 1, they add up to 0. So again, b0 is free, so I'm going to take b0 is free. So we take b0 to be 1. Now, when you collect the terms in the other series, the coefficient of x to the power n minus 1 becomes 2 n minus 1 n minus 2 bn plus 3 n minus 1 bn minus 1 bn, and then we have 2 bn minus 2. So we have bn minus 2 equal to, I'm sorry, bn is equal to minus 2 bn minus 2 divided by, this is 2n squared minus 6n plus 3n, so minus 3n, and the constant terms will cancel out. I have a minus 4, plus 4. I'm sorry. This is plus 4 minus 3 minus 1, so they add up to 0. So this is for n greater than or equal to 2. So B2, wait. Okay, where is B1 then? Oh yes, of course. I forgot one term here. Here in the last series, I put n equals 0 to get minus b0 x to the minus 1, but I should also put n equals 1. So I also have the term, okay, I'm sorry, for n equals 1, I have minus b1. Just b1, because x to the power 0 is 1, and then n starts from 2. So b0 is free, and the term minus b1 should be 0, so b1 is 0. Okay, so b2 is minus 2b0 over 4, 8 minus 6, 2. So minus b0, this is minus 1. B3 is minus 2b1 over something, so that's 0. B4, again, if you use this formula, it's 1 over 10. B5 is going to be 0 again. B6 is going to be minus 1 over 270, and B7 is 0, and so on. So the second solution, x to the power minus 1, B0 is 1, B1 is 0, B2 is minus 1, so minus x squared, B3 is 0, B4 is 1 over 10, x to the 4, B5 is 0, B6 minus 1 over 270, x to the 6, and so on. So some power series times x to the power minus 1, and now the general solution, C1, Y1 plus C2, Y2. And remember, this is on the interval x greater than 0. For x less than 0, you can work it out similarly. The lines are going to be the same, just replace x with minus x, that's all. Okay, so this is the only case of regular singular point that we are going to consider when the solutions of the roots of the initial equation roots are two distinct real numbers whose difference is not an integer. In this case, we can figure out the power series for the two roots. We figure out two power series, so we get two solutions, and we write the general solution as a linear combination. So that's all for power series solutions. Next time, we will discuss Laplace transformation. Okay, stay safe, stay healthy. See you next time. Or I'll not see you, but talk to you next time.